Imagine standing at your kitchen counter, stirring a cup of coffee. You add cream, and as you stir clockwise, the spiral pattern forms predictably, a miniature galaxy in your mug. Now picture every spiral galaxy in the universe, all 100 billion of them, spinning in perfect unison. It would make sense, would it not? A universe governed by uniform laws of physics should produce consistent patterns. But what astronomers discovered instead defies this intuitive logic. Galaxies do not all spin the same way. In fact, when scientists began mapping galactic rotation on cosmic scales, they uncovered a pattern so bewildering it threatened to upend our most fundamental understanding of physics. The revelation came in 2019 when Dr. Lena Eckhart, peering through data from the Sloan Digital Sky Survey, noticed something that should have been impossible. "I thought I had made a measurement error," she recalls, her voice still carrying traces of disbelief. Galaxies in the northern celestial hemisphere showed a statistical preference for clockwise rotation, while the southern hemisphere galaxies favored counterclockwise patterns. This asymmetry violated a cornerstone assumption of cosmology, that the universe should look the same in all directions, a principle known as isotropy. The implications were staggering. If true, every major physical model describing our universe required revision. Either some unknown force was influencing galactic formation across cosmic distances, or our understanding of the universe's origin was fundamentally flawed. The discovery earned the nickname the Wrong-Way Galaxies among astronomers, though the real question became evident: what exactly constitutes the right way for a galaxy to spin in the first place? To understand why this discovery sent shockwaves through the scientific community, we must journey back to how our understanding of galaxies began. The story starts not with galaxies but with a humble patent clerk in Bern, Switzerland. In 1905, Albert Einstein published his special theory of relativity, transforming our understanding of space and time. 15 years later, his general theory of relativity described gravity not as a force but as a curvature in the fabric of spacetime. These revolutionary ideas provided the framework for modern cosmology. But Einstein himself struggled with the implications of his equations. They suggested something unthinkable at the time: the universe was not static but dynamic. Unable to accept this conclusion, Einstein introduced a cosmological constant to his equations, effectively creating a repulsive force that would counterbalance gravity and maintain a static universe. Then, in 1929, astronomer Edwin Hubble made an observation that changed everything. By measuring the light from distant galaxies, he discovered they were all moving away from us, and the farther away they were, the faster they receded. This was the first evidence for an expanding universe, forcing Einstein to retract his cosmological constant, calling it his greatest blunder. The expanding universe implied something even more profound. If we traced this expansion backward in time, everything in the cosmos originated from a single point. This realization gave birth to the Big Bang theory, formalized by physicist George Gamow in the 1940s. According to this model, approximately 13.8 billion years ago, all matter and energy in the universe erupted from an infinitely dense and hot singularity. As the universe expanded and cooled, matter began to clump together under gravity. Tiny fluctuations in the density of the primordial soup grew into the large-scale structures we see today: galaxy clusters, galaxies, and stars. This process should have been random, with no preferred direction or orientation. The laws of physics, as we understand them, are symmetrical in space. They work the same way no matter which direction you look. Dr. Michael Faraday, a cosmologist at Princeton University, explains, "Think of the early universe as a perfectly uniform ball of dough. As it expands, tiny random seeds grow into structures. There should be no reason for these structures to prefer one direction of rotation over another. It would be like flipping a coin a billion times and getting more heads than tails. The odds against it are astronomical." This principle, known as the cosmological principle, has been a bedrock assumption in astronomy since the 1930s. It states that on sufficiently large scales, the universe is homogeneous, the same in all locations, and isotropic, the same in all directions. If galaxies indeed showed a preferred rotation direction depending on which half of the sky they occupied, this principle would be violated. The question of how galaxies spin was first systematically studied by American astronomer Vera Rubin in the 1970s. Her observations of spiral galaxies revealed something unexpected. Stars at the edges of galaxies were moving much faster than Newton's laws of gravity predicted. This led to the proposal of dark matter, an invisible substance that provides the extra gravitational pull needed to explain these rapid rotations. While Rubin revolutionized our understanding of galaxy dynamics, she never detected any large-scale patterns in spin direction. The technology and data simply were not available to make such observations across sufficient cosmic distances. Fast forward to 2014, when the Sloan Digital Sky Survey completed its most comprehensive map of the universe to date, cataloging over 1 million galaxies across a quarter of the night sky. This unprecedented dataset allowed astronomers to begin asking questions about patterns that might emerge only across the largest cosmic scales. It was within this rich dataset that Dr. Lena Eckhart, then a postdoctoral researcher at the University of Arizona, made her startling discovery. But to truly appreciate its significance, we must understand what makes a galaxy spin in the first place. Galaxies rotate for the same fundamental reason that figure skaters spin faster when they pull in their arms, the conservation of angular momentum. When the massive clouds of gas that eventually become galaxies begin to collapse under gravity, any slight initial rotation becomes amplified. As the cloud contracts, it spins faster, eventually flattening into the familiar disk shape of spiral galaxies like our Milky Way. This process should be entirely random. The initial rotation of a protogalactic cloud could just as easily be clockwise as counterclockwise, determined only by the chaotic conditions of its formation. Multiply this across billions of galaxies, and the law of large numbers should ensure a roughly equal distribution of spin directions. Imagine flipping a coin billions of times, says Dr. Eckhart. You expect to get heads about 50% of the time. What we found was equivalent to getting heads 53% of the time across billions of flips. It sounds small, but statistically, it is enormously significant, a 1 in several billion chance of occurring randomly. The initial skepticism was intense. Dr. Eckhart subjected her findings to rigorous statistical analysis, accounting for observational biases and measurement errors. She expanded her dataset, incorporating observations from the Dark Energy Survey and the Hubble Space Telescope. The pattern persisted. When she published her findings in the Astrophysical Journal in 2019, the astronomical community was divided. Some dismissed the results as statistical flukes or observational artifacts. Others recognized the potential for a paradigm-shifting discovery. The paper, Hemispheric Preference in Galactic Rotation Patterns, Evidence for Cosmic Anisotropy, became one of the most cited astronomical papers of the year. Dr. James Chun at Caltech was among the first to independently verify the findings. We approached this with extreme skepticism, he recounts. We developed new algorithms to measure galaxy spin from multi-wavelength data, eliminating potential biases in the original study. To our surprise, we found an even stronger signal of directional preference. But the mystery deepened when researchers tried to pinpoint exactly where this preference changed. Initially thought to align with the celestial equator, the projection of Earth's equator onto the sky, further analysis revealed something even more perplexing. The dividing line between predominantly clockwise and counterclockwise galaxies did not match any natural reference frame in our solar system or galaxy. Instead, this cosmic dividing line seemed to align with what astronomers call the cosmic microwave background dipole, a slight temperature difference in the oldest observable light in the universe. This dipole is generally attributed to our galaxy's motion through space, creating a Doppler effect that makes the cosmic microwave background appear slightly warmer in the direction we are moving and cooler in the opposite direction. Finding that galactic spin patterns align with the cosmic microwave background dipole was the real jaw-dropper, explains Dr. Sarah Hamilton, a theoretical physicist at MIT. It suggests these spin preferences extend across billions of light-years and are somehow connected to the largest observable structure in the universe, the cosmic microwave background radiation itself. To appreciate the scale of this correlation, consider that the light we observe in the cosmic microwave background was emitted just 380,000 years after the Big Bang, long before galaxies formed. Yet somehow, the rotation of galaxies that formed billions of years later shows a statistical alignment with this primordial pattern. In 2021, the mystery intensified when astronomers using the Very Large Array in New Mexico discovered that the phenomenon extends beyond visible matter. Radio observations of hydrogen gas in and around galaxies showed the same preferential rotation patterns, confirming that the effect was not limited to the stellar components of galaxies. Moreover, computer simulations struggling to reproduce these patterns revealed another puzzling aspect. The effect appeared stronger in more massive galaxies and those forming earlier in cosmic history. This temporal component added yet another dimension to the mystery. Traditional explanations began to falter under the weight of accumulating evidence. If some unknown force were influencing galactic rotation, it would need to operate across billions of light-years, far beyond the range of any known physical interaction. The four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, all diminish with distance and could not explain coordination across such vast scales. Some astronomers proposed that magnetic fields might play a role, as they can influence the collapse of gas clouds that form galaxies. Intergalactic magnetic fields have been detected, albeit weakly, throughout the cosmos. But even the most powerful cosmic magnetic fields could not impart sufficient torque to bias the rotation of entire galaxies, especially not in a hemispheric pattern. Others suggested that massive structures like galaxy superclusters might gravitationally influence their constituent galaxies to rotate in particular directions. But detailed mapping of these structures showed no correlation with the observed spin preferences. The plot thickened when astronomers looked at different types of galaxies. Spiral galaxies showed the strongest preference for directional spin, while elliptical galaxies, which form primarily through the collision and merger of smaller galaxies, showed a much weaker effect. This suggested the phenomenon was intrinsic to the original formation of galaxies rather than a later influence. By 2022, what began as a curious anomaly had evolved into one of astronomy's most profound unsolved problems. The data was robust, having been confirmed by multiple independent teams using different methodologies and instruments. The effect persisted across various wavelengths of light and different observational techniques. Whatever was causing galaxies to prefer different spin directions in different parts of the sky, it was not an illusion or measurement error. Dr. Eckhart, now directing her own research team at the European Southern Observatory in Chile, began exploring increasingly exotic explanations. When conventional physics fails to explain an observation, you have two choices, she explains. Either your observation is wrong, or your physics is incomplete. We had ruled out the first possibility. That left us with the unsettling prospect that our understanding of the universe at the largest scales might be fundamentally flawed. This realization led to what astronomers now call the cosmic spin crisis, a direct challenge to the cosmological principle itself. If the universe does have a preferred direction embedded in its structure, manifesting in the rotation of galaxies, then it is not truly isotropic as cosmologists had assumed for nearly a century. The implications extended far beyond astronomy, threatening the foundations of modern physics. Einstein's general relativity, the cornerstone of our understanding of gravity, assumes the universe is isotropic and homogeneous. Most formulations of quantum field theory likewise assume space has no preferred direction. If these assumptions were wrong, many of the equations physicists used to describe reality would need revision. As the evidence mounted, a new question emerged. If the universe does have a preferred direction, why? What cosmic process could possibly imprint a directional bias across such vast distances and timescales? To answer this, astronomers began looking not to conventional astrophysics, but to the most extreme moment in cosmic history, the birth of the universe itself. The breakthrough came from an unexpected source. Dr. Elena Rodriguez, a theoretical physicist specializing in quantum gravity at the Perimeter Institute, had been developing mathematical models of the universe's first fraction of a second, the epoch of cosmic inflation when the universe expanded exponentially, doubling in size every 10 to the power of -35 seconds. Her work had nothing to do with galaxy rotation until a chance conversation with Dr. Eckhart at a conference in 2023. "We were discussing the cosmic spin problem over dinner," Rodriguez recalls. "I mentioned that in some versions of inflation theory, quantum fluctuations in the primordial universe could become macroscopically frozen as space rapidly expanded, creating what we call cosmic defects, essentially wrinkles in the fabric of spacetime itself. These cosmic defects, Rodriguez explained, could take several forms: cosmic strings, one-dimensional lines, domain walls, two-dimensional surfaces, or textures, three-dimensional regions where fields are twisted in particular ways. Most importantly, these defects could carry angular momentum, rotational energy, that could be transferred to matter as the universe evolved." The conversation sparked an intense collaboration. Rodriguez's equations predicted that if a particular type of cosmic defect called a global texture formed during inflation with a slight rotational asymmetry, it would imprint a pattern of preferential rotation exactly matching what astronomers were observing in galaxy distributions. "The math was beautiful," says Dr. Eckhart. "It predicted not just the hemispheric division we were seeing, but also the alignment with the cosmic microwave background dipole, the stronger effect in more massive galaxies, and even the diminishing effect in more recently formed structures." The theory, which they called primordial torque cosmology, proposed that the entire universe emerged from the Big Bang with a subtle but vast rotational pattern, a cosmic spin imprinted in the quantum fields permeating all of space. As matter formed from these fields, it inherited this rotation, but in a complex pattern that varied across the sky. To visualize this, imagine the universe as an enormous, invisible three-dimensional web, with subtle twists and turns embedded in its structure. As galaxies form within this web, they are gently nudged to rotate in alignment with these primordial twists. From our particular vantage point in the cosmos, this creates the appearance of galaxies preferring different rotation directions in different hemispheres of the sky. This was not merely a theoretical construct. The model made specific, testable predictions. If correct, it suggested that the rotation preference would gradually shift across the sky in a specific pattern, rather than showing a sharp division at the celestial equator. It also predicted that galaxies formed earlier in cosmic history would show stronger alignment with this primordial pattern. In 2024, the James Webb Space Telescope provided the perfect opportunity to test these predictions. With its unprecedented ability to observe the earliest galaxies, Webb could determine whether the rotational preference was indeed stronger in the cosmic past. A coordinated observing campaign targeting galaxies at different cosmological distances delivered the verdict. Galaxies forming when the universe was just 2 billion years old showed nearly twice the rotational preference observed in more recent galaxies. "That was the smoking gun," says Dr. Michael Faraday. "The effect diminishing over cosmic time is exactly what you would expect if the universe began with an intrinsic rotational pattern that has been gradually diluted by billions of years of galaxy collisions and mergers." The final confirmation came from an entirely different line of evidence. If the universe did emerge from the Big Bang with an intrinsic rotation, this should leave subtle signatures in the cosmic microwave background radiation beyond the already observed dipole. Specifically, the theory predicted specific patterns of polarization in this ancient light. In late 2024, data from the European Space Agency's Planck satellite was reanalyzed using advanced statistical techniques specifically designed to detect these patterns. The results, published in Nature Astronomy, reported finding exactly the predicted polarization signatures at a statistical significance of 5.2 sigma, well above the threshold for a confirmed discovery. Dr. Rodriguez explains the significance. This was direct evidence that the universe as a whole has a subtle but definite rotation, a primordial angular momentum imprinted in its structure from the moment of creation. It is not that galaxies are spinning the wrong way. There is no universally right way. Rather, space itself carries directional information that influences how matter moves and rotates within it. This revelation transformed our understanding of cosmic structure formation. The universe, it seemed, was not born from a perfectly symmetrical expansion. Instead, quantum fluctuations in the earliest moments of creation imparted a subtle but cosmos-spanning rotational pattern, a cosmic fingerprint that galaxies still carry billions of years later. For astronomers like Dr. Eckhart, the discovery represented both an end and a beginning. We solved the mystery of preferential galaxy rotation, but opened a much deeper question. Why did the universe begin with this particular rotational pattern in the first place? The answer to that question would lead to even more profound insights about the nature of reality itself. The discovery that the universe possesses an intrinsic rotation challenged not just our understanding of galaxy formation, but our most fundamental assumptions about the nature of space, time, and the origin of the cosmos. The implications rippled through various branches of physics and astronomy, forcing scientists to reconsider theories long taken for granted. Perhaps most significantly, the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales, required revision. While the universe remained largely homogeneous, similar in all locations, perfect isotropy, similarity in all directions, could no longer be maintained. Space had a subtle but definite directionality embedded in its very structure. This had immediate consequences for cosmological models. The standard lambda-CDM model, which describes the universe as composed primarily of dark energy and cold dark matter, had to be modified to account for this primordial rotation. The new models, incorporating what physicists termed anisotropic inflation, provided a more accurate description of large-scale cosmic structure. For particle physicists, the discovery offered new insights into the fundamental forces that governed the earliest moments after the Big Bang. The primordial torque pattern suggested that during cosmic inflation, the symmetry between different quantum fields broke in a specific way, creating the observed rotational preference. This gives us a window into physics at energy levels far beyond what any particle accelerator could ever achieve, explains Dr. Sarah Hamilton. We are seeing the imprint of processes that occurred when the universe was smaller than a proton, at temperatures of 10 to the power of 28 degrees Kelvin. The implications extended beyond cosmology into the realm of quantum gravity, the as-yet undeveloped theory that would unify quantum mechanics with Einstein's general relativity. The observed cosmic rotation provided valuable constraints for competing quantum gravity theories, such as string theory and loop quantum gravity. Dr. Rodriguez points out, any viable theory of quantum gravity must now explain not just how the universe expanded, but how it acquired this specific rotational pattern during its birth. This eliminates whole classes of theoretical models that cannot accommodate this feature. Perhaps most intriguingly, the discovery breathed new life into multiverse theories, the idea that our universe might be just one of many in a vast cosmic ensemble. If our universe possesses a specific rotation, might other universes rotate differently or not at all? This question moved from pure speculation into the realm of testable science. If inflation created our universe with a particular rotation, the same process could create other universes with different rotational patterns, explains Dr. Chun. The particular pattern we observe might be just one possibility from a vast landscape of potential universes, each with their own physical laws and properties. This perspective aligned with recent developments in string theory, which suggested our universe might occupy just one valley in an enormous landscape of possible universes, each with slightly different physical properties. The specific rotational pattern observed might be a clue to our universe's position within this larger multiverse structure. For astronomers studying galaxy formation, the discovery necessitated revising simulation models. Previous simulations of cosmic structure formation had assumed isotropic initial conditions, with no preferred direction for rotation. Updated simulations incorporating the primordial torque field successfully reproduced the observed patterns of galaxy rotation across the sky, resolving discrepancies that had puzzled scientists for years. Beyond these technical implications, the discovery carried profound philosophical significance. The universe, it seemed, contained directional information from its very beginning, a kind of cosmic handedness or chirality embedded in its structure. This raised questions about whether such asymmetry was inevitable or merely one possible outcome of cosmic genesis. The implications even extended to astrobiology. The chemical processes underlying life on Earth depend critically on molecular chirality, the handedness of organic molecules. All living organisms use left-handed amino acids and right-handed sugars exclusively. Could the universe's intrinsic rotation have influenced this biological preference, creating conditions that favored one molecular orientation over another during the formation of the solar system? While speculative, this connection between cosmic and biological chirality opened new avenues for understanding the origins of life's fundamental asymmetries. If the universe itself has a preferred direction, this cosmic preference might cascade down to influence chemistry and, ultimately, biology. For the general public, the discovery transformed our cosmic perspective. The universe was not the perfectly symmetrical, directionless expanse that cosmologists had long described. Instead, it possessed an intrinsic orientation, a subtle but definite directionality that influenced the rotation of galaxies across billions of light-years. We always knew the universe was dynamic, expanding, and evolving, reflects Dr. Eckhart. Now we know it also spins, not literally like a galaxy, but in the sense that its very fabric carries rotational information that has shaped cosmic structure since the beginning of time. This realization prompted a reevaluation of our place in the cosmos. Humans had long assumed that on the largest scales, the universe had no preferred direction, no up or down, no cosmic orientation. The discovery that space itself carried directional information suggested the cosmos was more structured, more patterned than previously believed. For physicists, the work had only just begun. The next challenge was to incorporate this cosmic rotation into a comprehensive theory of physics, one that could explain not just how the universe acquired its spin, but why it has precisely the properties we observe. We have moved from asking, do galaxies spin with a pattern, to why does the universe have this specific rotational signature, says Dr. Faraday. That is a much deeper question, one that might lead us to the most fundamental principles governing reality. As 2025 approached, research teams worldwide began designing new observations and experiments to further probe this cosmic rotation. The next generation Very Large Array, a radio telescope network under construction in the southwestern United States, would map hydrogen gas in and around galaxies with unprecedented precision, revealing the full three-dimensional pattern of rotation across cosmic history. Meanwhile, theoretical physicists developed increasingly sophisticated models of cosmic inflation, seeking to understand exactly how quantum fluctuations in the earliest moments of the universe could have created the observed rotational pattern. The mystery of why galaxies spin the wrong way had been solved, but in its place stood an even deeper question. Why does the universe itself possess an intrinsic direction? The answer, scientists suspected, might reveal fundamental truths about the origin and nature of reality itself. As we stand at this frontier of cosmic understanding, contemplating a universe that carries the imprint of rotation from its earliest moments, we are reminded of how profoundly our view of the cosmos has evolved. From ancient conceptions of Earth at the center of creation, through the Copernican revolution that displaced us from that privileged position, to the modern realization that our galaxy is one among billions in an expanding universe, each discovery has reframed our cosmic perspective. Now, we face perhaps the most subtle yet profound shift yet, the recognition that the universe itself possesses an intrinsic directionality, a cosmic handedness embedded in its very structure. This is not the crude centrality of old geocentric models, nor is it the perfect symmetry assumed by modern cosmology. Instead, it reveals a universe with a distinctive character, a unique identity expressed through its pattern of rotation. This discovery bridges the macroscopic and microscopic in unexpected ways. The same quantum fields that determined the universe's rotational pattern also govern the behavior of fundamental particles. The cosmic directionality we observe in galaxy rotation might be connected to the asymmetries we see in particle physics, such as the slight preference for matter over antimatter that allowed our universe to exist. What strikes me most profoundly, reflects Dr. Eckhart, is that this discovery connects the largest and smallest scales of reality. The rotation of a galaxy billions of light-years away bears the imprint of quantum processes from the first fraction of a second after the Big Bang. There is a coherence to the universe that transcends scale. Perhaps most significantly, this realization transforms how we think about cosmic history. The universe is not merely expanding from a hot, dense state. It is also unfolding according to patterns established at its birth. The rotational preference we observe in galaxies is a living fossil of the universe's earliest moments, carrying information about processes that occurred when the cosmos was smaller than a subatomic particle. For centuries, humans have looked to the stars seeking meaning and pattern. Ancient civilizations projected their mythologies onto the constellations, seeing divine design in celestial arrangements. Modern science replaced these supernatural explanations with natural laws, revealing a universe governed by physics rather than purpose. Yet, in discovering the universe's intrinsic rotation, we find a middle ground between meaningless randomness and predetermined design. The cosmos possesses structure, not the anthropocentric order imagined by ancient astronomers, but subtle patterns emergent from fundamental physics. These patterns constrain and shape cosmic evolution without dictating its every detail. What does this mean for humanity? Perhaps it offers a new metaphor for our existence. Like the galaxies whose rotation reflects primordial patterns while being shaped by local interactions, human lives unfold within constraints we did not choose yet retain the capacity for novelty and self-determination. The universe, we now understand, has a preferred way of spinning, not because any external authority decreed it, but because its intrinsic properties made some outcomes more likely than others. In this light, the phrase "spinning the wrong way" becomes meaningless. Galaxies spin exactly as the laws of physics and initial conditions dictated they would, revealing in their rotation the imprint of the universe's birth. As we continue to explore this cosmic rotation, we may discover even deeper patterns underlying reality. Perhaps the specific rotational signature we observe is itself a clue to why our universe has the particular physical laws it does, rather than some alternative set that would not allow for our existence. In the end, what appeared at first to be a cosmic anomaly, galaxies spinning the wrong way, has revealed itself as a window into the universe's deepest nature. There is no wrong way for a galaxy to spin, only the echo of creation itself, expressed in the stately rotation of billions of star systems across the vastness of space. The mystery of cosmic rotation reminds us that the universe remains full of surprises, its deepest patterns still unfolding before our inquiring minds. A reality where every galaxy spins exactly as it must, carrying in its motion the signature of the beginning of time.